Hello and welcome to the 34th lecture of this short course called Behavioral Theory of Systems with a view towards data driven control. So, um, we were trying to find out B that generates that contains that generated the date a trajectory W of whose only finite information is available, right. And we said that in order to get to this B by calculating left kernels of various Hankel matrices, we need to first derive certain properties about B. In fact, in particular, we need to find out some properties about these restrictions. Okay. So, we had already proven that the dimension of these restrictions are given by k plus 1 times q, where q is the number of variables, m. M is the input cardinality of the system, plus m0 plus dot 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 up to mk, where these mk's are defined as the dimension of the null space of the k minus first observability matrix by the kernel of the kth observability matrix. And we also argued from these observability matrices that these numbers mk's are nothing but rank differences, the difference between rank of OK and the rank of OK minus 1, and from there we found out that mk's must be non increasing. Okay. Now, from these, and also let me remind you that m infinity is equal to 0, which means rho infinity is equal to m, and summation I going from 0 to infinity of mi is equal to n, right. Okay. And remember that all these m numbers are bigger than or equal to 0 always, because of this because these are defined like this. Okay. Now, I said that it will be important for us to know the dimension of BK pub. Remember, BK pub is nothing but vector space representation of NK. All right. What is dimension of BK pub? Now, by just rank nullity theorem, simple use of rank nullity theorem tells me that dimension of BK pub will be k plus 1 times q, that is the number of variables, minus dimension of BK. Yeah, but okay, that is k plus 1 times q minus dk, that is equal to k plus 1 times q minus k plus 1 times m minus m0 minus m1 minus dot 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 minus mk. Now, q, as you know, is equal to m plus p, correct, input cardinality plus output cardinality. So, then therefore, from here and here, if I do this subtraction, I am going to get k plus 1 times p minus m0 minus m1 minus dot 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 minus mk. Okay. Now, if k is bigger than or equal to k, that is the saturation point, where this capital K is the smallest such number beyond which m is equal to 0, these mk's are equal to 0. Yeah, it is mk k is equal to 0 for all k bigger than or equal to k, and this k is the smallest such k, smallest. So, if then if k is bigger than or equal to capital K, then we have dimension of bk pub equal to, remember it is k plus 1 times p minus m0 minus m1 minus dot 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 minus mk, but mk is 0 no, for k bigger than or equal to capital K, 0. So, that means I have summed it up for all. That means this is the same as k plus 1 times p minus summation I going from 0 to infinity mi. That means this is equal to k plus 1 times p minus n. Right. So, the dimension of bk pub is this number. That also means that dimension of nk, that is all those annihilating polynomial row vectors whose degrees are less than or equal to k, if you collect them together, that forms a vector space, and that vector space has dimension exactly equal to k plus 1 times p minus n, yeah, provided this k is bigger than or equal to the saturation point. Okay, now so our, as I said, we were actually after conditions which will guarantee that column span of Hankel matrix L created from the data is equal to B L. That is what we are after, condition on the data. Okay. So, okay, this is equivalent to proving left kernel of this guy is equal to BL pub. In general it is this containment, but it is this. Okay. What we will do is, in order to get to those conditions which will guarantee that this will happen, we will first assume that what if it is not, yeah, can we reach to some sort of a contradiction. What if it is like this, what if it is strictly, what if there is strict containment like this, what will happen then. Okay, that is very good. BL is nothing but NL, right, BL pub is nothing but NL, is the all those annihilating polynomials of degree less than or equal to L. This implies, however, if the strict containment is there, then this strict containment implies that there exists a row vector R0 R1 dot 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 up to RL. What is this size? This is q size, this is q size, this is q size. So, L plus 1 times q, such a vector, which is in the left kernel of HL, but the corresponding, let me call it R xi, defined as R0 plus R1 xi plus dot 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 plus RL xi to the power L. Such a thing, this R xi is not in NL, yeah, which of course contains in N. So, that means I do not have R xi. So, I am saying that R xi, this R xi is not an annihilator. Let me spell it out clearly, not an annihilator. So, let me write it there, yeah, write it on the next page. That is R xi is not an annihilator. This will lead to some contradiction. What sort of contradictions? Now to go to such contradictions, what we will do is we will go to a safe zone, we will go to a safe place where we can actually play around with these numbers. See, ultimately we just have the data and we are writing them in terms of this Hankel matrices, right. So something you can expect that the conditions which will guarantee that this happens will have something to do with the rank of these matrices. So rank of some Hankel matrix must be something, that is the kind of conditions that can happen, right, that can be there. So for that what we will do is we will go to a safe zone where the numbers do not vary anymore. What does that mean? Of course we go to a point beyond the saturation point, right. So once we go beyond the saturation points, we can actually precisely say various numbers, and once we have those numbers, some inequality rank nullity theorem basically we can use to get our results, get our conditions, right. So where were we? Beyond this point, yes, Bk pub, that is dimension of Nk, satisfies this beyond the saturation point. In this case we will do the following. We will look at H L plus N of the data, yeah, of the given data. So should I put a W hat? It is sometimes customary to put a W hat to distinguish that there is a particular trajectory. Yeah, so let me just did I use H before? I did use H L. Okay, so let me just reiterate. It's fine. It's W. It's okay. So H L plus N W is where I am going. Okay, I am putting this W specifically because the condition that will come in terms of U, the input. Yeah, we will come to that very soon. But let us put this H L plus N W here to be absolutely precise. So I am looking at this H L plus N. Now why did I look at this H L plus N? What is so special about H L plus N? See, now the index is L plus N, right. So when I look at its left kernel, I am actually looking at B L plus N pub, which also is the same as annihilators of degree less than or equal to L plus N. That is all very good, but what is L plus N? I say L plus N is always beyond the saturation point. Why is that so? Even when L is not there, L is equal to 0 even, then also this will be true. Why is that so? Okay, what is this K? K is the smallest beyond which, so K is let me define it precisely. K is by definition equal to minimum of all what should I use, all kappa in Z plus such that M k is equal to 0 for all k bigger than or equal to kappa. So this is my time axis, let us say, yeah, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and so on. K really is the saturation point. Why? If this is the saturation point, then beyond this, whenever any small k that I take which is beyond this 5, which is beyond this 5, I will have M to be equal to 0. So M is 0 in this whole range, Mk is 0 in this whole range, right. What are these kappas? So kappas are all these numbers. This can be a kappa, this can be kappa, this can be kappa, because kappa says that beyond this the numbers are 0, this Mk numbers are 0. So among those kappas, the minimum one that I am taking, that is my capital K. So that is the saturation point. I claim that this is always true. Yeah, why is that so? Notice, I have M0 plus M1 plus M2 plus dot 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 up to Mk to be equal to n, and each of these M0, all of them are bigger than 0 now. M1 bigger than 0 dot 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 up to Mk bigger than 0, because it becomes 0 sorry, I should have k minus 1. Yeah, from mk onwards it becomes 0, right. That is the definition, right, greater than or equal to, yes. So, this sum is equal to n and they are bigger than 0, because capital K is the smallest point from beyond which from which point onwards mk values are equal to 0. Before that they should be bigger than 0, strictly bigger than 0. So, these numbers are strictly bigger than zeros, correct. So, then what can you say about this number n? This number n obviously has to be bigger than k, yeah. Otherwise you see n will be exactly equal to k if you have see, if this is 1, this is 1, this is 1, this is 1 and so on. So, if all of them are equal to 1, all of them are equal to 1, then I have k to be exactly equal to n, right. K to be exactly equal to n if all of them are equal to 1, yeah. If all of them are equal to 1, then this is equal to k and that is equal to n, right. If m0 equal to m1 dot 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 equal to mk minus 1, all of them equal to 1, then we have k equal to n, but the moment any of them is strictly bigger than 1, we will have k to be strictly less than n, because these numbers are bigger than or equal to 1, yeah, strictly bigger than 0. So, that is why in any case k will always be less than or equal to n, and that is what we wanted to prove, is not it. Yeah, we wanted to prove that L plus n is bigger than or equal to k. In fact, n is bigger than or equal to k. So, that means this HL plus n is always beyond the saturation point, this L plus n. So, therefore, we have the following, we have n L plus n, which is the same as B L plus n pop. The dimension of these guys, now I have a clear handle on these numbers. The dimension of this is equal to, what was it, L plus n, sorry, plus 1 times p minus n, right. That is the number that we get, that is the dimension that we get. Okay. And now coming back to what we were doing, once again we look at this guy, yeah, we have a handle on this now, on the dimension of this guy. Now, we look at this HL plus NW and we look at this left kernel of HL plus NW will still contain B L plus N pub, yeah, obviously. If it contains this, notice that it will also contain something more. I look at this R xi, right. How did I define this R xi? Remember, R xi is in the left kernel of HL, right. This guy is in the left kernel of HL. So, if it is in the left kernel of HL, then notice that if I look at R xi, I look at xi times R xi, I look at all the way up to xi to the power n times R xi. All of these polynomials are coming from R xi and they are degrees. If I now look at their degrees, R xi had degrees less than or equal to L, is not it, less than or equal to L. R xi had degree less than or equal to L. So, when I go all the way up to n, xi to the power n, this has degree less than or equal to n plus L plus n. So, that means each of these guys are actually inside the left kernel of HL plus NW, because what is HL plus NW? We had HL, no, beyond that we keep on shifting. So, therefore, if R xi kills this guy, then any shifted version of R will also kill these further guys. So, therefore, R padded with zeros and then R shifted with other empty parts padded with zeros and so on, all of them will be there in the kernel of HL plus NW. Yeah, I hope I'm making sense here, right? Or in other words, you know, R xi is this R0 dot 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 up to R RL. This kills HL. This implies, notice that R0 dot 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 up to RL, this times HL plus 1 is equal to 0, and this is nothing but xi times R xi. Yeah. So, once you understand this, the fact that all of these guys are in the left kernel of HL plus n, that should be clear. Okay, great. So, this all of these vectors are there because this is a vector space. Now, if we look at the vector space generated by these guys, the subspace generated by these guys, that is also contained in let me not rewrite, let me just let me not write it here, let me just rewrite. Let me just rewrite on the next page, otherwise it becomes a little clumsy. So, what I am saying here is that the row is the span, sorry, I am too sloppy, R xi R xi dot 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 up to xi to the power n R xi. This R is a subspace of left kernel H L plus n of W. Great. So, now I have two subspaces of left kernel of H L plus n, namely this one and this one. But if that is so, then that also implies B L plus n perp summation with R xi times R xi dot 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 xi to the n R xi, this subspace, both of them are contained in left kernel of H L plus n W. Okay, right. Now, now we are going to make a claim. We are going to make a claim that this subspace and this subspace, they have a non-trivial intersection. Claim B L plus n perp intersection R xi dot 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 up to xi to the n R xi. This intersection is non-zero. Some non-zero vector, so non-zero vector will be there, which is in here as well as in here. Why is that so? Suppose not. Suppose not. I mean, they having a non-trivial intersection will help us. In what way? And if they have non-trivial intersection, then I can do something. Then I can do something interesting. Yeah. What is that I can do interesting? Well, before we prove the claim, let us look at that interesting bit. Yeah. If the so I am not going to prove the claim right away. I am going to first prove a consequence of the truth of the claim. Yeah, let us say we do not do that. Yeah, little aside. Yeah, consequence of the claim. What is the consequence of the claim? If so, consequence of the claim, if R xi R xi dot 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 up to xi to the n R xi, if this guy, if this subspace intersection B L plus n perp is indeed not equal to 0, then this means there exists a linear combination, namely alpha 0 R xi plus alpha 1 xi R xi plus dot 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 alpha n xi to the n r xi, yeah, this must be equal to some f xi, a row vector of size 1 cross q, times r xi. What is r xi? B is equal to kernel of R sigma, the ground truth. We have such a matrix R xi kernel representation, because when I say that this intersection is non-zero, that means there will be such a non-trivial linear combination which will belong to B L plus n pub, belong to B L plus n pub. But what is this? This is n L plus n. That means in particular this must be an annihilating vector, and every annihilating vector must belong to the row span of this matrix. So that is why this must be in the row span of R xi, and that is why we have this. But when we write alpha 0, alpha 1 xi R xi, alpha n xi to the n R xi, I can just collect alpha 0 plus alpha 1 xi plus dot 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 up to plus alpha n xi to the power n and call it small f xi, and what we have here is that f xi times this R xi must be equal to some capital F xi into R xi. But now notice, f xi is a, I am assuming, is some polynomial, right? That polynomial will have some complex in general root. If we are at a root, so suppose lambda is a root of f xi. If lambda is a root of f xi, then f lambda is equal to 0. So then in that case, f lambda r lambda capital F lambda r lambda must be equal to 0, because this is equal to 0. Yeah, but can this product be 0? Remember, R xi is factor left prime, because I have assumed controllable behavior. Because it is factor left prime, what we know, this must be full row rank for all lambda, for all complex numbers lambda, this is full row rank. If it is this full row, if this is full row rank, then the only vector that can be in its left kernel is the 0 vector. So that means f at capital lambda is also 0. What does that mean? That means f lambda can be written as xi minus lambda times some g lambda, isn't it? Likewise, f lambda, oh sorry, my bad, what did I write? I write all sorts of weird things. This means that f xi is xi minus lambda times g xi. That means xi minus lambda must be a factor of f xi, because f lambda is equal to 0. So the 0 row vector, that means every element must contain xi minus lambda as a factor, so I can pull out. Okay. But f xi of course is some xi minus lambda times g xi. So but we had f xi r xi equals capital F xi r xi, right? And now I have from this xi minus lambda g xi r xi is equal to xi minus lambda capital G xi r xi. This I can cancel out. Yeah, these are non-zero polynomials, and so I have this now, that g xi r xi is equal to capital G xi r xi. But if it is a non-constant polynomial, I can go even further. I can find out a root of g xi and do exactly the same trick and further reduce the degree. You see, from f xi to g xi the degree has reduced by 1, certainly by 1. Yeah, not equal to, the degree of g is not less than or equal to f xi, it is strictly less than degree of f xi, unless f was a constant, unless I was not able to pull out a factor. Yeah, the moment I can pull out such a non-trivial factor, the degree will strictly reduce by 1. If the degree reduces by 1, and if I can do the same trick again, so the degree will reduce even further and keep on reducing until and unless I have this g xi coming out to be equal to a constant. If that is so, then that means in fact non-zero constant, yeah, r xi in fact is equal to some f xi. I should not write f, let us say some, okay, some f tilde xi, oh capital I was writing, no, yeah, because it is a row vector, f tilde xi r xi. But that is a contradiction. Why? Because that means r xi is an annihilator. But what did we start with? We started with the fact that, okay, let us take such an oops, where is it? Yeah, before yeah, I wrote it, that is R xi is not an annihilator. So, when this strict inequality is there, that means R xi is not an annihilator. That is how we started. So, but now I am saying R xi must be an annihilator. What was the thing? That was, what is the crucial point that made it happen? This claim. Yeah, the moment I have this non-trivial intersection between this and this, at a safe point, at a safe zone. The moment at the safe zone I have this, it must mean that I reach a contradiction. So, which means this is not an annihilator that I have written, that is not wrong. So, it will be an annihilator, and we will have this equality which in turn would be this equality. So, all I have to do is that find out conditions under which the claim is true. Find out conditions under which the claim is true. So, if we have a condition under which claim is true, that would be a sufficient condition to guarantee that Hankel HL column span will be exactly equal to BL. So, all I have to do is find out condition under which this is true. This is true. How can I do that? Very simple. Count the numbers, count the dimension of this and count the dimension of this. If they have no intersection, then this sum will have dimension equal to this plus this, the dimension of this plus the dimension of this. What is that number? This number I know is L plus n plus 1 times P minus n. And what is the dimension of this guy? This is a single row vector. This as a vector, this as a vector, all of them are linearly independent. You can check. Yeah, over the field of real numbers. If you now look at linear combinations of this guy, that equal to 0 would mean that this polynomial must be 0. So, if you take a linear combination of this guy, that is just alpha 0 plus alpha 1 xi plus dot 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 up to alpha n xi to the n times a polynomial row vector. If this is the 0 row vector, this being a non-zero polynomial row vector means that this polynomial must be equal to 0, must be equal to 0. If this polynomial is equal to 0, then that means the linear combination is the 0 linear combination. So, these guys are linearly independent. So, this guy has dimension equal to n. So, if there is no intersection, then this plus has dimension equal to this L plus n plus 1 times P. Okay. Can we compare it with the dimension of this guy? Yeah, what is the dimension of left kernel of L plus n times L plus HL plus n W? Dimension of left kernel of L plus n W. What is this size? This size is L plus n plus 1 times P. Yeah, sorry, why did I write P? It's times Q. That is the number of variables present here. Okay. Okay. And so, minus rank of H L plus n W. Yeah, what will be this rank? On the left hand side, if there is no intersection, then the number is L plus n plus 1 times P. This is actually equal to P plus L plus n plus 1 times M, right? And because it is contained, it is like this. So, I must play around with the number here of this guy, which will give me the condition. So, that this leads to some sort of a contradiction. That means this number is turning out to be strictly bigger than whatever number we have on the right side. If we can do that, then we are through. Yeah, but I think I have already run out of time. Although it's getting very interesting, we will just continue with this idea when we come back for the next lecture. All right, we will continue with this, and we will see some consequences of this particular condition that we will have on this, and it will turn out that this is the condition which is known as the persistency of excitation. Yeah, the so called fundamental lemma of data driven control. This and many more is what we will see in the next few lectures. You take care of yourselves very good. Then till then, bye.